Okay, this is like the third time that I'm filming this because I keep messing up, but my name is Katherine Liu, and today I'm going to be doing Chapter 2, number 60. Okay, so the number 60 basically asks, okay, so you're standing at the edge of a well, and you're going to throw this rock from rest down into the well. Or rather, you're going to drop the rock into the well, and it's going to fall however deep the well is, and it's going to hit the water, make a splash. That splash is going to reverberate, and it's going to come back up to you at the speed of sound at that temperature. So in my diagram that I drew here, you can see kind of what's going on. Well, the sound is technically inside, but I drew it outside just to make it less confusing. My positive direction is upwards. The depth of the well I decided to call H for height. I labeled the surface of the water, which is right here. This is the surface of the water. I labeled that at 0, at position 0. So actually right up here where the rock is initially, that's going to be whatever H is, as indicated here. I've also said that since the rock is being dropped from rest, our initial velocity is, our initial velocity is 0 meters per second. And this is the positive direction. Okay, so I'm going to begin my process now. So part A is asking for how deep is the well? So basically, what is H in essence? I'm going to start with my acceleration equation because this rock, it's falling at a constant acceleration due to gravity. That constant acceleration is negative 9.8 meters per second squared. It's negative 9.8 because it's going in the downwards direction where upwards is positive. Okay, I'm going to anti-differentiate and I'm going to get velocity. My velocity is going to be negative 9.8 meters per second squared times time, and then plus initial velocity. In this case, don't have an initial velocity. It is 0. So we do have one, but it's 0. So this is actually our final velocity equation. Excuse me. Okay, I'm going to anti-differentiate one more time, and I'm going to get our position time equation. So then this is going to turn into negative 4.9 meters per second squared times time squared, and then plus initial position. As I said before, our initial position is right here. That is the value of H. So I'm going to change this to H. Now this is the equation right here. That's the equation that we're going to be using in solving for H right here. Right, but before we go into solving for H, I'm going to talk a little bit about T. So we want the amount of time for this rock to fall exactly to 0. We want that moment. We want to represent that moment just before the splash, because at that time, the rock has fallen H meters. Does that make sense? So if it's fallen H meters at that time, then we want to figure out what exactly that is so that we can figure out what H is. But the time total that's given in the question is 2.40 seconds, but that number represents the amount of time for the fall and the amount of time for the sound put together. So if you want me to write that in kind of like an equation form, 2.40 seconds is equal to the time of the fall plus the time of the sound to come back up. So if we just want that fall, remember, because we're looking for this moment right here, we're going to get, you just move that over, so 2.40 seconds minus the time it takes for the sound to come back up. And how long does it take for the sound to come back up? Well, then that can be, remember how distance equals rate times time? Yeah, so if you want time, then you could do distance over rate. Well, we're going to do that same thing here. So the distance, this distance that it travels to go up, that's h, isn't it? And then the rate at which it travels going upwards, that's going to be our 336 meters per second. If you think about it, the meters on top from the h and the meters right here, those two are going to cancel each other out, and then this seconds is going to swing up because it's in like the denominator, and that's going to give you an overall units of seconds right here, which makes sense because you want your fall time to be in seconds. Okay, so then using this, we're going to go back to this equation. I shouldn't draw arrows because that's confusing. Okay, so right here, that's the moment that we're tracking right now. The distance that you traveled, your position, is actually exactly 0, right? And then you're going to have your constant out front. And then for your time, the time that it took for you to get to here, that's the amount of time that it took for the rock to fall, right? So we're going to plug that in. And then we're going to have that plus, we're going to have that plus h on the outside. Okay, with me so far? Okay, now this, it factors into a really ugly quadratic formula, quadratic equation, but I actually have a program on my calculator, which I'm not going to show you because that would take excessive amounts of time. So I'm just going to tell you that h gives two values. One is 26.37 meters, and the other one is a negative value. So obviously we don't want the negative value because, well, we know that this is a parabola shape, right? According to the acceleration and this position time graph, we know that it's a downwards parabola. So if you have the parabola going like that, then there's probably going to be one negative value and one positive value for the same time. In this case, obviously we don't want a negative value because, making sense, your initial height is not going to be below 0 because then it'd be falling up. So then we're going to take the positive value of h, which is this. Okay, so basically, actually that is part A. You just figured out how high how deep the well is. Part B is slightly more, it's actually about the same. So part B is asking you, okay, if you were to neglect sound, the speed of sound, and how long it took for sound to travel back up, well then how long what is the percent error? So to do that, we need to first find how long it takes, or what the depth of the well would be calculated as if we did not account for sound. So we're going to go back to this equation. So x is equal to negative 4.9 meters per second squared times time squared plus h. In this case, we're assuming that this upwards, that is covered by my book, sorry, but that the upwards movement of sound is not there, that it did not happen. So everything is going to stay the same because you still traveled all the way down to 0, but we're assuming that the sound is instantaneous, like you hear it instantly. No time is lost. So we're going to have that 0 at this time, in quotation marks, and then we have our negative 4.9 meters per second squared. Our time in this case is going to be the full 2.40 seconds. And then we have our h on the side. This results in an h of 28.22 meters. If you plug that into your calculator, that's what you get. So obviously these two numbers are different. We're going to calculate the percent error now. I'm going to move this up a little bit more. Okay, so percent error. Percent error is your theoretical minus actual, or the absolute value of, over the theoretical times 100%. So in this case, our theoretical is this, which is what it's supposed to be. So like, and then our actual is going to be this number, because that's what we got in, that's what we got by like experimenting. So like that's the wrong one. That's the one with the margin of error. Then the perfect answer the theoretical one, that's going to be put on the bottom, so 26.37 meters. And then these meters are all going to cancel, and times 100%. Oops. I'm using my books as a stand for my phone. Okay, so I'm just going to plug that into my calculator. Oops. 26.37 minus 28.22 divided by 26.37. So ignoring the negative on that because I didn't do absolute value, that is going to be 7.02% error, which is actually kind of a lot if you think about it. Okay, and that's my video. That's how you do question 60 in chapter 2. Thanks for watching.